Special right triangles. Now we're going to discuss two special right triangles, and the test writers are absolutely in love with these. Why? Because both have the property that with very little information you can get all kinds of information. You can figure out all the sides and angles and figure out other things just from a little bit of information. So they love the fact that they can just give a little information and then you're expected to find all the rest. So these are very good triangles to know about. Triangle number one. The first is an isosceles right triangle. Think about that. It's a right triangle, has a right angle, but isosceles means two sides, the two legs, are equal. So the angles also must be equal, so it must be a 45, 45, 90 triangle. The two legs have equal length, and the hypotenuse is larger than either leg, though less than the sum of the legs. So let's consider a 45, 45, 90 triangle with legs that happen to have length of 1. We can find the hypotenuse with the Pythagorean theorem. So that's just 1 squared, or 1, plus 1 equals 2. And so the hypotenuse is the square root of 2. That was just one 45, 45, 90 triangle, but the big idea is that all others in the world are similar to that. So they all have the same ratios. So they all have two equal legs, and for all of them, the hypotenuse is root 2 times the length of the leg. We could think of the sides as the leg equals s, and the hypotenuse equals s times root 2. We can refer to this triangle in three different ways: the isosceles right triangle, the 45, 45, 90 triangle, or the 1, 1, root 2 triangle. You have to know this triangle very well, but do not simply memorize it. Instead, make sure you understand why each set of properties implies all the others. The more you can just start with one property and derive the others, the more you will really understand this triangle. Notice that we divide a square in half along the diagonal, we get two of these. This makes it very easy to see that the diagonal of a square equals the side times the square root of 2. That's also a handy fact to know. We can also divide a square into 4 of these triangles, and the hypotenuse of each is on the side of the square. So we're going to pause here for a minute to take a detour from geometry to discuss numbers. We're going to talk about rationalizing denominators. Now, those of you who watched the Powers and Roots module, this should be familiar to you, and this may be some helpful review. Some of you are coming directly to this lesson from a particular question, and you may be completely unfamiliar with this idea. I'm going to give a very brief overview here, but really, if this is a new idea to you, you probably should watch some of the lessons in Powers and Roots to get familiar with all the background of this. So, special right triangles often involve square roots and may involve fractions, so we have to consider the case of what to do if we have a square root in the denominator. A square root in the denominator is considered problematic for a variety of reasons. For example, the test will never list fraction answer choices with a square root in the denominator. So even if the correct answer is 7 over root 5, the test is never going to list an answer choice in that form. We fix this problem simply by multiplying the fraction by the radical over itself. So in particular, 7 over root 5. We want to get rid of that square root in the denominator, so we're going to multiply by root 5 over root 5. Of course, we can multiply by anything over itself, because anything over itself equals 1. Now notice what happens in the denominator. We get root 5 times root 5. Well, by definition, the square root of 5 times itself equals 5. And in the numerator, I just get 7 times root 5. So 7 root 5 over 5, that is considered the proper way to write this, without a radical in the denominator. And again, this was just a brief example, a very brief overview of the topic, rationalizing denominators. It's kind of a whirlwind tour of the idea. If this is new to you, brand new to you, probably a very good idea to watch the lesson on rationalizing, a full lesson on this one particular idea. In this lesson, we're just going to move forward and assume that you know this idea now. Here's a practice problem. Pause the video and then we'll talk about this. Okay, so we have a square We have a 45-degree angle in that triangle, so that is an isosceles right triangle there. And we want the perimeter of the square. Very interesting. Well, first of all, we know that Kn, that's the leg of the triangle, it's also the side of the square, that times root 2 equals the hypotenuse, jk. So we certainly can say that Kn equals jk over root 2, or 6 over root 2. And immediately what we're going to do, because we have a radical in the denominator, we're going to rationalize. We're going to multiply that by root 2 over root 2. Then I'll get 6 root 2 over 2. 6 over 2 cancels to 3. So 3 root 2. So that is the rationalized expression for the length of Kn. Now the perimeter is just 4 times that. 4 times 3 root 2, or in other words 12 root 2. And we go to the answer choices and we select answer choice D. The second triangle. For this, we will begin with an equilateral triangle in which each side has a length of 2. This triangle, while very symmetrical, is not a right triangle, of course, but we can create a right triangle by drawing an altitude from point A, essentially cutting the triangle in half with a line down the middle. As in any isosceles triangle, this altitude will bisect the angle at A and bisect the opposite side. So here it is with that line drawn, and now we can actually see the triangle that interests us in purple on the side there. The angle at B is one of the original 60-degree angles of the equilateral triangle, and the hypotenuse AB is one of the original sides. The angle at 30 degrees is the bisected angle, and DB is a bisected side. So we have the length of two sides. We have a leg of 1 and a hypotenuse of 2. Let's just say AD equals H. We can find H with the Pythagorean theorem. 2 squared plus 1 equals 1 squared plus H squared. In other words, H squared equals 4 minus 1 or 3, and H equals the square root of 3. So that is the length of AD. So sometimes this is called the 30, 60, 90 triangle. Sometimes it's called the 1, 2, root 3 triangle. It's very helpful to remember the relationship that this triangle has with the whole equilateral triangle from which it comes. In fact, one of the best ways to understand what's going on is kind of to draw the dotted other half of the full equilateral triangle so you can visualize it. As with the 45, 45, 90 triangle, any 30, 60, 90 triangle is similar to this one, and the sides are proportional. So we could say that the hypotenuse is always twice the length of the short leg. The long leg is always root 3 times the short leg. Now that we know the 30, 60, 90 triangle, we can create a general formula for the area of an equilateral triangle with side S. Create an altitude which divides the whole triangle into two 30, 60, 90 triangles. So the hypotenuse is S, so ML equals S over 2. And Km, the altitude, would have to equal S root 3 over 2. So Km is the altitude, and JL, which is equal to S, is the base. So of course area is 1/2 base times height, 1/2 S times S root 3 over 2, and this simplifies to S squared root 3 over 4. That is the formula for the area of an equilateral triangle that has a side of S. Now this is a very handy formula to know, but do not memorize it. Instead, make sure you can understand the argument and reproduce the result on your own. In other words, start with the equilateral, build the 30, 60, 90 triangle, and wind up with this formula. And if you can produce this same formula again and again, then you really understand it. Here's a practice problem. Pause the video and then we'll talk about this. All right, we want to find the perimeter of this triangle. It is a 30, 60, 90 triangle. Well, the short leg is half the hypotenuse, so the short leg is 4 root 3. The long leg is root 3 times the short leg. Well, 4 times root 3 times root 3. Well, root 3 times root 3 is just 3. So that's 4 times 3, which is 12. And so the hypotenuse is 4 root 3 plus 8 root 3, which is 12 root 3, plus 12. Here's a harder practice problem. Pause the video and then we'll talk about this. Okay, in the diagram, HJLM is a square. And we have GH, that slanty side, is 10. And of course JK, because it's symmetrical, JK would also have to be 10. We have two 60-degree angles, so we have two 30, 60, 90 triangles, one on each side. So first of all, we can find the proportions. We know that GM equals 5. We know that HM equals 5 root 3. So one triangle would be 1/2 base times height, but we have two triangles here. So the area of the two triangles together is just going to be base of the triangle times the height, which is 5 times 5 root 3, or 25 root 3. That's the area of the two triangles. The square has a side of 5 root 3, so we square that, and we get 75. So the entire area is the square plus the two triangles, 75 plus 25 root 3. One special triangle, the isosceles right triangle, has angles of 45, 45, 90 and sides of 1, 1 root 2. The other results from dividing an equilateral in half and has angles of 30, 60, 90 and sides of 1, radical 3, and 2. We can use these patterns in proportional reasoning to solve a variety of problems.